So then it is my pleasure to start with the last technical lecture for this term, and we will now kind of combine some of the techniques that we have seen in order to come up with the system for recursive state estimation, and especially in order to solve the simultaneous localization and mapping problem using an extended Kalman filter. So Kalman filter and extended Kalman filter is something we discussed last week. It's a technique for recursive-based filtering for the Gaussian case. So we assume that all our distributions are Gaussians. And we assume that we have nonlinear models, but we're going to linearize those models. And what we want to do is we want to estimate the location of features or landmarks in the environment, as well as the location of the sensor with respect to those landmarks. So we want to come with a map which contains the landmarks and an estimate of the current position of our sensor of our mobile platform, and we want to use the extended Kalman filter framework for doing so. So we basically start with the EKF algorithm and then kind of explain how the individual matrices and transformations look like so that the approach does what we want, estimating the location of our sensor and the location of our landmarks in the environment. So again, goal is build a map of the environment and localize the sensor in the environment, and we want to do that online. That means we don't want to collect all the data beforehand and then do our estimation. We want to be able to do that in kind of incremental fashion or online fashion. So as soon as the next sensor measurement comes in, we want to update our belief, and we are only interested in the current position of the sensor. So we're not necessarily interested about the history, where that was in the past. We're interested in what's the current state of the system, plus the location of the landmarks in the environment. So why is this central, especially this online capabilities? So online capabilities are needed whenever we have systems or robots that want to use this map in order to navigate. So whenever you have to make a decision, for example, where to go, you need to have an idea where you are and what the environment looks like. And therefore, that's actually pretty relevant for a large number of different applications. It's one of the key building blocks for any autonomy that is related to to the environment, to some actions in space. So whenever we have a system which needs to travel from A to B to do something, to achieve something, to bring something from A to B, that is important. Even if we have a manipulation system which needs to know what the environment looks like, where objects are in the environment, they need to know something about the geometry. And some of those systems yet you know, for example, this is one of the indoor cleaning robots that you can actually buy today or already since a couple of years. This is a system which actually has kind of Swiffer towels below it, so it's not a Hoover. These systems basically use a technique which is very, very similar to the extended Kalman filter here. They're not using the Kalman filter. These guys are typically operating in information space. This is kind of the dual representation of the Kalman filter, where we don't use moments, so mean and covariance matrix, to do the estimates, but use the information vector and the information matrix, so the inverse of the covariance matrix, to represent the belief. But from the estimation point of view, this is actually very, very similar to what the Kalman filter does. They're underwater robotics, for example. This is from Australia, where they do a lot of monitoring of the seabed and coral reef monitoring, which are systems which use techniques presented here. This is actually a group which was very, very active in Kalman filtering and estimating the location of those underground vehicles using Kalman filters. Also for space application or underground applications, it's important to know where those systems are with respect to their surroundings in order to plan trajectories to go from A to B or to build consistent maps or come back with a map from the seabed. Okay, so what we have and what we want is something you already know. So it's exactly the same as for the general recursive-based filter. So we have a set of control commands which emit a control to the platform, like whatever, travel a meter forward, something like that. So we have control commands and we have observations up to time t. And we're currently at time t. We start with t equal 1 and advance the discrete time one step further. For example, whenever a new measurement arrives, we kind of increment t by 1. And what we want is one of a map of the environment, typically referred to as M. This can be simply a list of feature locations. And we want to know, in general, the paths of the platform, but we are typically interested in the online platform. That means we are only interested in in the current pose. So we're using an EKF, which is a recursive based filter, and we are only estimating xt, so the current state of the system. We're not necessarily interested in the past because this doesn't affect my decision-making process typically. So I have a map and I know where I am right now, and this is the most important element for decision-making. As I said, we want to use the EKF. That means we have a prediction step and we have a correction step. The prediction step takes into account our motion model, and the correction step takes into account our observation model or measurement model. And we want to do this for the Gaussian case, so everything is Gaussian, and our models are at least not too far away from the linear case. So they are nonlinear, but we should get a good result if we linearize them, so not very, very severe nonlinearities. So in terms of the state estimation problem that we want to solve, so we're not going over all poses, only interested in the most recent pose. That's why he has only a t and not whatever from 0 to t or from 1 to t. And given our observations and our controls. And if we plot this as a Bayes network, so these are all the variables involved. All the variables which are shaded in gray, light gray are those which are known. These are the observations, are the control commands. And what we want to estimate is the location of the platform and the map of the environment. And everything which has a dark gray box around it are those quantities that we estimate. So these are unknown variables where the robot was in the past, but I don't care about it. I'm only interested in estimating the current pose of the system and the map of the environment. This is kind of one way for representing that. You can read those errors as influences. So the pose at time t is influenced by where the system was before, and it is influenced by the control command which was executed. And itself influences on what I'm going to measure, and what I'm going to measure is also influenced by where the features are in the environment. So these type of networks allow you to very easily and intuitively model and represent dependencies or independencies of individual variables. Because you can read those errors as influences or directly influences, and then you can say which variable influences which other variable. So the motion model is basically consists of taking these two errors and estimate, given I know those two guys, how do I go here? And the observation model says, given I know the whole state, so I know these, how do I actually represent this distribution? So this is what the motion model and what the observation model looks like. And this is kind of just one way for representing it and for illustrating those dependencies. Okay, that's enough for the introduction. Let's jump into the Kalman filter, this kind of 5-line algorithm that we've seen here and discussed last week. And I'll say, okay, how do those individual functions look like? So how does G look like? How does Jacobian look like? How does our measurement function look like? So our expected observation, how then the Jacobian looks like. And once we specified all that, we can actually directly implement this algorithm and actually discuss some of the properties of this algorithm. Okay, so the first thing, how does our mean and our covariance matrix look like? Or this guy over here. So the estimate from the previous belief. How does that look like? How would you do that? So you're sitting there starting your MATLAB implementation, and I say, okay, how does the variable mean, mu and sigma look like, the mean, the covariance matrix? Yeah?
First, you don't have a map. So your position is maybe just 0, 0.
Okay, we can start at 0, 0, 0. So x, y, 0, orientation 0, just our local reference frame where we start at the platform. The first 3 dimensions of the mean are x, y, and 0. And that, once I have a map, how do I need to augment that mean vector? So I need to store the location of the features or the landmarks I want to estimate in the environment. Assuming we're in a 2D world, it will be the x and y coordinate for every feature. X, y coordinate of feature 1, x, y coordinate of feature 2, x, y coordinate of feature 3. If I would live in a 3-dimensional world, it would be x, y, z. feature 1, x, y, z of feature 2. Okay? So that's how my state vector looks like. The first 3 dimensions are the robot's pose, or the sensor's pose, the x and y location of landmark number 1, so the M1 means landmark number 1, the x coordinate, landmark number 1, y coordinate, landmark n, x coordinate, landmark n, y coordinate. Just stack them all up. Okay. How could I initialize this vector? So you said 0, 0, 0 for those dimensions. What about the others? You can also set them to 0. But I don't know anything. The only important thing is that the covariance matrix then should be the variance value is infinity along the main diagonal.
So how do you know how many landmarks there are?
That's a very valid point. There are 2 ways for doing that. One way is you simply start, what you would do in practice, you would start with the 3-dimensional vector and would simply extend it as soon as you see a new landmark, or you already allocate whatever n landmarks, and then you simply extend the state vector if that is needed. It depends on how efficient your the implementation should be, so how much memory you have or how expensive it is to expand those states. But kind of from the mathematical point of view, we would now assume we have a fixed length of n, because just make the math a bit easier, and we are not needing to extend our vector. But in practice, you would simply increase the size of your vector and your of your mean vector and your covariance matrix appropriately. Okay? So, state vector, robot's pose, pose of landmark 1, position of landmark 2, position of landmark n. That means, Gaussian belief, this is our mean vector. So now this is a 3-dimensional variable. These are 1-dimensional variables. And this is a 3 by 3 matrix over here. And this is a 2n by 2n matrix over here. And this is 3 dimensions 2n, 3 dimensions 2n. Okay? So nothing very special. Sometimes it's actually written like this. Just a very compact form. So again, 2n dimensional, 3 dimensional, 3 by 3, 2n by 2n, and then corresponding 2n by 3 or 3 by 2n. Okay? All done. State vector specified, and we know what our covariance matrix look like, at least the structure. So then we have to do a few things in the EKF algorithm. We need to be able to compute the predicted state. So we need to use the model that we have to evolve the state to compute the predicted belief, update mean and covariance matrix accordingly. We need to be able to compute an expected measurement. So given what we know already, and given where the platform is, we need to compute what we are expecting to observe. This is our measurement function. Mapping from this known state to the observation. This is our predicted observation. Then we need to retrieve the real measurement and make the data association saying, okay, the predicted measurement and this measurement, they belong to each other, and compute the difference between them, between the predicted measurement and the real measurement, to then perform the update. So this is kind of the prediction step, and this all is part of the update step. Just broken up a little bit. So the next thing we can do is just to have a kind of illustration how that works. So the prediction step. So given we started here, and this is our initial uncertainty, we make a forward movement. Let's say we go over here. And this is so our uncertainty according to the prediction, not taking into account any observation. The first thing, if we are interested in computational efficiency, is which variables need to be updated for that step. These are actually those variables which are highlighted here in green. So if I just move my sensor forward or my robot forward, the only thing that changes is the state of the robot. So I'm not changing the landmarks. I'm not manipulating the environment, as long as I don't bump into something. But that's something I'm not going to consider here. So if you move forward, the thing which gets updated is the first 3 dimensions from our state vector. So only 3 dimensions are updated. That's something good. That's something which is fast. Constant number of updates that I need to do here. Okay? If I look into my covariance matrix, however, I need more updates. So of course the uncertainty here changes because I execute a motion that increases the uncertainty. But there's also a correlation between the landmark locations and the robot's pose, which is going to change. So I need to update those states. It means, however, if I have n landmarks in the environment and n is large, this operation depends on n. So even a motion update depends on the number of landmarks that exist in the environment. This is something which can be problematic. Because just in order to move a little bit forward, I need to update a potentially large number of states if I have a large number of landmarks over here. Okay? Something to keep in mind. I only move one element a little bit, just 3 dimensions out of a potentially large number, but I need to update a number of elements which is linear in the number of landmarks which are out there. If I have a huge map all over Germany and I just move a little bit here, I need to update a potentially very large number of different elements. Okay, is it kind of clear? Good. So the next thing is we do a measurement prediction. So, okay, we are now in that state here, and according to my map, that's kind of a landmark and the uncertainty associated to this landmark. That's just my current belief. So what will I measure? I have to compute my predicted measurement. Say, okay, I'm here. It's my estimate at the moment, my predicted belief. So I actually should obtain this as a measurement. Just saying, this is my mean estimate. This is my mean estimate of my feature. Let's say I have a range bearing sensor, so a sensor which tells me where the object is in terms of its orientation with respect to the platform, and also I know the distance. So it will tell me something like whatever, 80 degrees to the left, 5 meters apart. I just can compute this based on the mean estimate of that feature and the estimate of the robot's platform. So it gets something like this. I take that state, take the feature location, and compute my predicted observation. So this is a prediction of my observation. And nothing is updated down here. Right? I'll just compute the predicted observation. Nothing changes. Okay, let's say now I take the real prediction from my measurement. This was just the predicted one. Now I take the real observation, so ZT, what my sensor tells me. And I may get something like this. So it's a little bit rotated to the left in this example over here. So what I need to do is I need to make the data association. That means I need to say, okay, those two observations are the same. I need to compare them. Right? Because in the EKF, line number 4, there was the update of the mean. And one of the expressions there was ZT minus H of the predicted mean. So this is the predicted observation. And this was the real observation. Okay? What I need to do is I need to compute this difference between what I was predicting and the difference between what I got in reality. It's exactly this expression in my EKF equation. And based on that, I compute the update of the mean and the update of the covariance matrix. And this leads to a new belief where you can see the uncertainties shrink because the observation provides me additional information. So I reduce my uncertainty typically through an observation. So you can see that I kind of reduce the uncertainty where the platform is here. And also about the landmarks. So I need to update potentially the whole state vector and the whole covariance matrix. This makes sense. So I simply measure something. I measure the environment. Depending on the landmarks that I measure, I need to update my whole belief because I get more certain about where the sensor is and more certain about where the landmarks are. Okay? It's kind of the overall kind of framework clear now. So far we have been working on a very high level. So just introducing the algorithm, introducing these steps. And now the goal is to dive more deeply into what we are doing now. And now going to every individual line of the EKF and say, okay, this matrix looks like this function looks like this in order to understand what's going on. But is everything clear up to that point? Okay, that's good. Okay, now we have to be a bit more concrete. We assume our platform moves on a 2D plane. So we only have x, y, and my orientation theta. We have a velocity-based motion model that basically means we control the rotational velocity and the translational velocity of my platform. So I can say move forward with a certain velocity or rotate with a certain velocity. So very, very simple movement, very simple drive. There are point landmarks in the environment, so I just measure the location of a feature in the environment. We have a range bearing sensor. That means it's not like a camera where we only obtain a bearing information. We already know the distance to that object. So a sensor which actually simplifies my life. I don't need to do triangulations. But you can see this as a stereo camera where you already have identified your feature points, you have triangulated that feature point, you get a Gaussian estimate where that feature is in the environment. We don't go into the details here. The only important thing is we get the orientation and we get the distance to that landmark. It's a range bearing sensor. Range for the distance, bearing for the orientation. And the other thing, we assume we have known data association. That we need to know if we see something, a landmark or a feature, we know to which feature this guy belongs in the map. So we can make this data association. This is given. Okay? And we assume we have a known number of landmarks. Let's say we know before and there are 100 landmarks in the environment and I only need to maintain 100. So I can initialize my state vector, my covariance matrix right from the start. Are those assumptions clear? Okay. Then let's go to the detail. We need to initialize our belief. We said already before, 0, 0, 0 for the pose, 0, 0, 0, 0 for all landmarks. And then we simply have to set a very high uncertainty about those landmark locations. So the initialization of my belief would look like this. The initialization, mu0, 0 vector, the covariance matrix. Zeros all over here. Actually, everywhere zeros except here on the main diagonal, there's always infinity. Because I have no idea where my landmarks are. Why do I have 0, 0 here? What does this mean? What does this 0, 0 mean in the first 3 dimensions over here? Yeah?
I'm in the center of the coordination system.
I started my platform and I define the starting pose as my reference frame with 0 uncertainty. So I start up the platform. Which is okay, I have no idea where I am, so I say, okay, here is 0, 0, 0 without any uncertainty, because it's how I define my reference frame. If I have an external reference frame given, I would need to initialize this. So those 3 guys and this matrix. So if I say, there's an external reference frame and I simply have an initial Gaussian belief, I would put exactly this initial Gaussian belief in, whatever, 1 meter, 2 meters, 90 degrees, and then some uncertainties of this initialization. But if I do it like this, it basically means I start at the platform and the starting location is the definition of the reference frame. And therefore, there's no uncertainty involved. But I have no idea where my landmarks are. So infinitively large uncertainty over here. Okay? Okay, so initialization is done. Now we have to look into the first line of this equation. And say, okay, this is clear. This is a mean vector as we had it before. So this function g needs to be specified. So we said it's kind of the velocity-based motion model. So I have a translational velocity and I have a rotational velocity I can set. So basically whatever, rotate 10 degrees per second and drive 1 meter per second forward. So we'll have kind of a movement which is forward and slightly rotating. And I can simply set that for discrete points in time. So from time t to t plus 1, I simply set one of those pairs, a rotational velocity and a translational velocity. So we don't need to go into the details how this motion model looks like. We can just look up basically the equation, how this is updated. So the new position is given by the old position plus an additional term, which involves sine and cosine, because it depends where I'm looking to, and has this factor of v is translational velocity, omega is rotational velocity. So this is a general equation where, as long as we don't move on a straight line, then the equation looks slightly different, but so because then omega t would be 0, but this is kind of the basic form, basically. Change the orientation just based on the delta t. Let's say every second I do that. So if I rotate with 10 degrees per second to the left, I will correspondingly update the orientation. Of course, the xy position also changes, but depending on where I'm actually looking right now. And this is then my function g. I call it g of xy theta because this is a three-dimensional function. And if I go back here, this function g maps actually from a 3 plus 2 n-dimensional space to a 3 plus 2 n-dimensional space. So this is kind of the high-dimensional state vector because it only contains a landmark. Therefore, I call it g xy theta. If I would just call it g, this would be kind of in the high-dimensional space. If I now want to specify g, how can I specify g based on this small g over there? So what is the function g doing with all the landmarks?
So it doesn't change.
Exactly. So I can expand that over here. No, only zeros would not be a good idea.
So zeros on.
Yes, so exactly. So, so we simply have the old landmark locations all over here, and this guy gets 0 everywhere here, right? Okay. So we can do this. So if we do this in MATLAB, you can quite easily say, oh, just change this block of the matrix and just change this block of the matrix. If you want to write this down in matrix form, this can be slightly more complicated. So what we can do in here is we said, okay, this is our high-dimensional state vector here. This is our previous state vector over here, high-dimensional. And then I have my function here, which was kind of the add-on, this part, in three-dimensional update. Then I have this matrix, which is 0 everywhere. It just has, so it's a 3 by 3 plus 2 n-dimensional matrix. All elements are 0 except of the 3 elements. So if I multiply this vector with this matrix transposed, I actually obtain the high-dimensional matrix where those changes are in the 3 diagonal element, the rest is 0. So therefore, this matrix Ft may look a little bit weird here, but it's just the reason is we need to move from these low-dimensional spaces to these high-dimensional spaces. So in MATLAB, you would probably just perform this update directly in your state vector. Anything which requires clarification?
I was just wondering if the ones are in this diagonal because we transpose it, and then you have like a backward diagonal of ones. Maybe it's okay.
No, it should be okay because it was still diagonal here and the zeros will go down here. So it should be okay. It should be fine. So the key thing is, so basically this matrix F has the form, you have the identity matrix over here and then all zeros over there. So if you transpose them, you still have the identity, the zeros go there. And so this is here, in this case, three-dimensional. And you have 3 plus 2 n dimensions over here. And then you have your, your update here, which is 3 and 1 over here. And so you transpose this matrix, and then you will, if you multiply then F transposed times your state vector over here, you obtain here your, what is actually x, what's in there, x sits here and 0 sit over here. Okay, perfect. So with this, we specified the first line, right? This is now our big function g. First line done. So if we've written here, this is our function g. You can very easily write that down, and then the first line is done. So we have our update over here. So I have to go to the next line. So 1 out of 5 done. Well, let's address the second line. What was this g over here? So is it, no, not the Kalman gain. Kalman gain was k. So this g, so this is just the prediction step. This is correction step. So it has to do something with this function. So it's a linearization of this function. So this is Jacobian. So the matrix containing the partial derivatives, because this is basically variance propagation, what we're doing here. Or error propagation for compute. Okay, so it means we need to compute the Jacobian of this function g. We specified g, so we now need to sit down and write down the Jacobians. If I see already that I have this form, let's go back. I have this form of my function g. I need to compute the first derivative of this function. That's what the capital G is. If I derive with respect to the landmark locations, this is just the mean vector, and we add zeros, so it's a one-to-one mapping. So the Jacobian is the identity matrix for all landmark locations, because basically I don't change them, right? It's just a one-to-one mapping. If I compute the first derivative of a direct one-to-one mapping, the Jacobian here is the identity. Okay? So for all the landmarks, that's the identity. That's easy. But here, those guys are nonlinear elements. You need to be able to compute the first derivative of these functions. And they will populate the 3x3 matrix. So if I compute the Jacobian of this, Jacobian will have this form. There's here a 3x3 block, which has some nonlinearities in there. So this is expected to not be the identity matrix. But everything down here is just the identity matrix, a 2n by 2n identity matrix, because I don't change my landmarks. The function g, leave the landmarks untouched. Right? So the only thing I need to focus my attention now on is actually this 3x3 matrix over here. So we need to compute this 3x3 Jacobian, just deriving with respect to x, y, and theta, only taking into account the dimensions x, y, and theta of my mean vector, or of the function g, sorry. Okay, so I take my function g, this was my function g, and I need to compute the first derivatives with respect to x, y, and theta, right? So I have a sum over here, so I need to derive these guys with respect to x, y, and 0, which is trivial because this is, again, the identity. And then I need to derive these guys with respect to x, y, and 0. So I can split up that as the Jacobian of this first block, simply the identity matrix. And then I have the first derivatives of this vector with respect to x, y, and theta. So I need to take this dimension, derive it with respect to x. Take this dimension with respect to y. This dimension with respect to theta. Then take the second line, derive this one with respect to x, with respect to y, with respect to theta. And this one over here. So we'll have 9 elements, 3x3. Okay, so what happens if I derive these lines with respect to x? Exactly. There's no x in there. It will be 0. What was y? Same. There's no variable y involved in these functions. If I derive it with respect to y, they're all 0. So the only thing which matters here, which is non-zero, is deriving these elements with respect to theta. And even not the last line. There's no theta involved in here. So I only have 2 elements which are non-zero. And I simply need to derive this with respect to theta. So the sine will change into a cosine, something like this will happen, but no black magic involved. So if I do this, I maintain my identity here. Everything here is 0, this is 0, and these are the elements that I obtain. Basically, sine and cosines change, and maybe a sine changes. Right? So I could put everything together. I have this matrix where I have 1 on the main diagonal, 1, 2, 1, and those are the 2 elements of the Jacobian which are non-zero. Okay? So, done. I'm ready with the Jacobian. I'm done with this line over here. So this is a constant, this is just the noise of my observation. This is what I have, my previous estimate, and I have this function g. And now I've written a few lines here to kind of prove the first picture I had on this introduction, where saying if I have the motion update, I only change parts of the covariance matrix that we have. And this actually shows exactly what happens. Okay, so this is just copy-paste from this line. And now I have to fill the matrix G, sigma, and G transpose. So this was my Jacobian. This was kind of the 3x3 block that we computed. And we have the identity on the main diagonal. So that's how it looks like. Then I have my covariance matrix. So here, uncertainty in the landmarks, uncertainty in the pose, and the appendices between those estimates. And I have the transposed Jacobian. If I transpose the identity matrix, nothing is transposed, and I have the transpose of this guy plus some matrix R. And so if I simply do this matrix computation, I see, okay, this part, so this is a 3x3 matrix, has this form of update. This block here does not get updated because it's just multiplied with the identity matrices over here. So therefore, this large matrix, and this is a 2n by 2n matrix, so potentially large, is unchanged. But here I multiply the 3x3 matrix with this 3 by 3 plus 2n matrix. 3 by 2n matrix. So this is kind of 3 columns and 2n, 3 rows and 2n columns, sorry. So I have the update here, I have the update here, I have the update here, but this part is unchanged. Yes, please. So what R, so it's a valid point, what is changed according to R? What R does, R is encoding the uncertainty of my motion. So just because I'm walking around in the environment, I'm not changing any landmark. Yes, so R can be seen as a matrix which has something on its 3x3 block and the rest is 0. Because the intention behind it is, if I do a movement, I'm only changing the location of my platform. I'm not changing the landmarks. So this is just the motion uncertainty. And therefore, so this matrix R is a matrix which has, let's say, some RT in, let's call it 3x3. And there's something in there. So this is a 3x3 matrix, but all the remaining parts are 0. Okay, so we are done with this line. Prediction step completed. Perfect. Next thing I need to do, I need to look to the prediction step. Right? Before we look at the prediction step, I actually want to write this down into an algorithmic form. So if you want to actually need to type that down as a MATLAB script, you know how to do that. So the first lines is, okay, I have to specify my matrix F, which is this weird function, which is one diagonal here, this weird matrix diagonal here, 0, 2n, zeros all over here. So then I can say, okay, my predicted mean is my original mean plus this function f transposed times the function g at the 3x3 function. I do the same with the Jacobian, so I can express the Jacobian exactly the same way via this function f. And then I need to update my covariance matrix. And what you see here is exactly what was written here, this RT. So there I was just calling this guy is RTX on the slide. So it's just the motion uncertainty in the dimensions which affect the position of the platform. So a 3x3 matrix. This is exactly the 3x3 matrix over here. And with this function f, I'm basically bringing it into this form. So just, of course, if you would be in MATLAB, you would do that differently. You would take your matrix RT, which initializes as 0, and then say kind of the first 3x3 block is updated accordingly. So you would probably not, in practice, generate this matrix as an inducer multiplication because you can directly write into the corresponding elements. Just kind of to have it mathematically sound, that's what would be the way the prediction step looks like. Okay? Okay, so let's look into the correction step. So we need to specify our predicted observation, and we need to, as a result of that, specify the Jacobian of this function. So which quantities matter for doing this computation? If my platform, I'm observing a landmark, which dimensions are affected by h? Or I need to know about. Do I need to know about the robot's pose? Yes, I need to do, that's correct. So it matters where I am, what I'm going to measure. What else do I need to know? The position of the landmarks, so x and y location of the landmarks that I'm observing. These are 5 dimensions. X, y, theta, landmark position x, landmark position y. So only 5 dimensions matter out of this large vector over here. So the locations of all other landmarks don't matter. So the important thing is, we will come to that in a second, this function h has only 5 dimensions which matter. The others are irrelevant for computing the predicted observation of a landmark j. I only need to know xy location of j. I'm not interested in the xy locations of all other landmarks. Right? Makes sense. If I want to know how far whatever this sign here is away, I don't care how far you guys are sitting away from me. Only this thing matters. Where I am and where this thing is. Okay. So let's revisit the assumptions that we did. We said, okay, we have known data association, so I always know which point or point feature I'm actually observing. So I know the index j of the landmark I'm observing. So if I have this variable CIT, means at time step t, this variable tells me which landmark is the ith observation receiving. So typically, I have whatever an observation in image, and I see multiple features. So this is kind of feature number 1 in the image, feature number 2 in the image. This is this index y, I. And the index j is to which index does this correspond in my state vector. So it basically tells me my ith observation, which dimensions of my mean vector is affected. So whatever it says me, this is the first feature, this is the 10th feature, this is the 100th feature that I've seen. So this is known data association. This is here encoded through this index variable c. So c tells me the correspondencies, that's where the word c comes from, between what I observe in my sensor data and what I have in my map or in my mean estimate. Okay? So what I need to do is, I need to compute the predicted observation. And here's a special case. What happens if I've never observed this landmark before? I've never observed the landmark before. My predicted observation, I can't compute it. Or it has a very, very large uncertainty, infinite uncertainty. So I need to think about how to initialize a landmark. I need to compute the expected observation or predicted observation, so what I'm expecting to get, in order to be able to compare it then with my real observation. And this predicted observation is exactly this function h, small h. Once I've specified h, I can compute the Jacobian, capital H. And then I just execute the equations as they're written down for the Kalman filter. Okay, so I said I have a bearing-only sensor. So in order to estimate what I'm observing, I say, okay, I simply take my knowledge of where I am, where I'm observing something like this wall over here. So I have a mean estimate of that wall, a mean estimate about myself. I know my orientation, so I'm actually able to compute what I should see. If I have no information about my landmark, I need to initialize it. So if I know I'm here according to my estimate, but I have no idea where this wall is because I've never seen it, I just get my first observation of the wall, I can't compute a predicted observation. So what I can do is I can just take this observation and actually initialize it, and then don't proceed with the update. Because I have just one observation, I have my observation noise, so I can actually initialize this landmark. And so this is something which I can do very simply. So I said, okay, that's where I am. So this is the predicted position at time t, the x dimension. So this is the x location of the sensor at time t, the y location of the sensor at time t. And then I have a measurement, that's what I physically measured, which consists of range and a bearing observation. So I know whatever I measured is according to the sensor, 90 degrees to the right. So I need to combine the 90 degrees to the right with my orientation, let's say 45 degrees to the right. So I have 90 plus 45 degrees, 135 degrees to the right. So what comes out here, the distance that I measured, and then the sum of that gives me the predicted location of the landmark J, its x and y coordinates. So I can very easily initialize this landmark, right? So I can compute where is a landmark given I'm here, and that's what I see. Because I know where I am, I know in which direction I measure the landmark, and I know how far it is away, so I can actually initialize this. Okay? So then the next thing, it's a bit more complicated, is to compute the predicted observation. So given, because it's kind of a different thing now. Now I know where I am, or I have an estimate where I am. I have an estimate where the landmark is, what I'm expecting to observe. Because I need to compute, again, this guy over here. So I need to take what I have observed in reality, compare this to what I'm expecting to observe. I now want to compute this function h. So this h, let's ignore that for a second here. This h, what I'm expecting to measure depends for range bearing sensor. Now this is sensor specific. It depends on how far I'm away from the estimated position, right? So if I want to estimate that here, so that I'm here, the landmark is this pole over here. So I need to know how far am I away from this location, right? So I can take my map and say, okay, 1, 2, 3, 4, 5 meters. So one of the quantity that will matter is the Euclidean distance between my current estimate and the estimate of the landmark. Okay? The second component that will matter, because I need to know, specify the orientation, will be where am I looking and what's kind of so where's the platform looking to, and at which orientation from the sensor is the landmark. So if I have, let's say, my optical axis of my camera goes in this direction, so this is whatever, 70 degrees. So I have these 70 degrees matter, and it also matters how I am oriented. So these are the two components which play a role in here. Okay, so what is this? Delta x, delta y. This is simply the difference in the x dimension between where the landmark is expected to be and where I am expected to be. So this is for x and y locations. So it's just the difference between the location of this pole over here and the x and y dimension where I am. Okay? So if I take delta transpose delta, I have the squared distance. If I then compute the square root out of it, I have the Euclidean distance. So the square root of q is nothing else than the Euclidean distance between my current estimate and the current estimate of the landmark. There's just the Euclidean distance. It's written in this form because later on, if we do compute the derivations of these expressions, actually those deltas and q's will pop up, and it's a nice variable substitution. That's why it's. But this is nothing else than the Euclidean distance. So this is the r of my observation, the distance. And then just specify the orientation. So the orientation depends what I'm observing, expecting to observe. I need to know where am I oriented to as a platform, and how, because this tells me how the sensor is mounted on that platform, and where in the sensor frame I'm observing something, or should observe something. And this depends on the difference in the x and y coordinates of my location and the pole, because with the aton function I can actually compute this angle. And I need to subtract to that where I'm actually looking to. So this just gives me the angle at which the sensor will see that landmark, given the known locations. And this is exactly my predicted observation, so this z hat I. So this is the predicted, what I'm going to predict, given the knowledge about where the landmark is and where I am, plus its orientation here. I can compute my predicted observation. And this is exactly my function h. So this here is my predicted observation. It will tell me at which distance and in which angle I will observe this landmark, given I'm here looking in this direction and the landmark is over there. Okay? So in order to compute the Jacobian, I need to compute the partial derivatives of this function with respect to all dimensions. So with respect to x, y, theta, x location landmark 1, y location landmark 1, x location landmark 2, y location landmark 2, and so on and so forth. What we said before, wait. Only 5 dimensions matters. The x dimension of the platform, the y dimension of the platform, the orientation of the platform, and the xy location of that landmark. All other landmark locations are irrelevant. So computing this Jacobian of h will be a matrix basically consisting of zeros, only a couple of non-zero elements. And these are those which are related to the position of the robot and its orientation and the position of the landmark. Okay? So we can now say, we compute the partial derivatives and we do this kind of in a low dimensional space. So we only take now here the dimensions into account that matter, those which are non-zero. And what matters is x, y, theta, and the x location of landmark j and the y location of landmark j. So all the others are 0. Right? That's what we said before. So what we need to do now is we need to take this function h, which is this one over here, so this is h, and derive this with respect to those 5 variables. So what's the shape, what is this Jacobian, what's the shape of this Jacobian? What kind of matrix? What by what? Which dimension does this matrix will have, this matrix H low? Yeah? 5 by 5, are you sure? Why 5 by 1?
Well, you have 5 dimensions of that one object you are observing.
Not really. What do I observing? What am I observing about my land? I have one object, that's true, but what do I observe?
Well, the x and y coordinates.
It's an x and y coordinate. So
The direction plus the coordinates of your sensor.
no, that's not what I'm going to observe. What I'm observing is the range and the bearing to the landmark. So it's a 2-dimensional observation. We have a bearing information, so the distance, and we have an orientation. Therefore, this has 2 dimensions. But I need to derive these 2 dimensions with respect to 5 variables, and that's where the 5 is correct. So it will be a 2 by 5 matrix. So this H will be a 2 by 5 matrix. And it consists of taking the first dimension of this function h. The first dimension of this function h was this Euclidean distance over here, what you see here. Derive it with respect to x. Derive it with respect to y. With respect to theta, m, j, x, m, j, y. So I have 5 dimensions and 2 dimensions here. Okay? Now I simply need to compute that. How do I compute the first derivative of this guy? Actually rather straightforward. So it's the chain rule I need to apply. Innere Ableitung mal äußere Ableitung. So compute the first derivative of this variable q, and then as q consists of delta square, and delta depends on the x and y location, and if I derive it with respect to x, so x is here exactly, this guy over here, this is the equation that I get. So first derivative of this, so this is q to the power of a half, will give me a half times 1 divided by square root of q. Then chain rule, this square is a quadratic function, so I have 2 times delta x, and if I derive this expression with respect to the mean, just minus 1 maintains, and this is the minus 1 over here. And I simply do this for all elements. So I do this with respect to x, y, the others, and do the same thing for the observation. So in the end, I obtain this Jacobian over here. You know, it's just it has such an easy form because of using those variable expressions. That's the reason why this may be counterintuitive q and delta has been defined, because then this expression gets easier. There's nothing else than computing all the partial derivatives of this function h with respect to x, y, theta, x landmark, y landmark. And I do this for the Euclidean distance. So what is my expected distance that I measure? And I do this with respect to the orientation. What is the expected orientation that I'm going to measure? Okay? Good. So we have this Jacobian. We said, okay, now we have this Jacobian only computed in those dimensions which matters. We again, very similar to this function f, need to map it into this high-dimensional space again. Now, however, we have not only the 3 dimensions, or the 3 dimensions here which are non-zero, we have 5 dimensions which are non-zero. 3 relate the robot's pose, will be very similar to what we've done here, but 2 will be sitting somewhere where the index corresponds to this landmark j. So at actually 3 plus 2 times j, and plus 1. Okay, this is how this function f looks like for mapping the feature. We have again our identity matrix over here for mapping the first 3 dimensions into this block over here. And then we have a couple of zeros over here. And then we have 2 elements here which are non-zero, and this is exactly the index of the j's landmark. So this is a dimension 3 plus 2 times j, and 3 plus 2 times j plus 1. Excuse me, these dimensions, and then zeros again. So all the landmarks which are unaffected, and these are the landmarks which are unaffected. Only one landmark matters. This is kind of the landmark j. So it's landmark 1, 2, 3, 4, 5, 6, 7 until j minus 1. Then landmark j plus 1 plus 2 plus 3, and so on and so forth. And if I execute this computation, I directly map it to my high-dimensional Jacobian. So h is specified. I now know how this high-dimensional Jacobian looks like. In this sense, I've specified everything I need to specify. This I have already. This I specified. Or this I specified, so I can transpose it. That's easy. This element, this is just my function q. This is my observation noise. So this is a noise. This is a 2 by 2 matrix in our case. There's simply the uncertainty in the range and the uncertainty in the bearing of my scanner. So this is a 2 by 2 matrix. So I can compute k directly. Then I have this expression over here. I have my observation. I have my predicted observation. Compute this element. I have k. Just need to add it to the mean. And here, same thing. I know k, I know h, I know the predicted belief. So I can compute all these things in a straightforward manner. So I can do all of that, and I'm done. Computed the new mean and the new covariance matrix of my belief. The only thing I need to know is h, also function h and Jacobian h. In this block over here, the rest follows directly. And the only thing I needed to do here is specify this function g and compute its Jacobian. If I again want to put the second block here down in algorithmic form, I can do this. So I have the uncertainty about my observation. So I have some noise in the range and some noise in my bearing observation. Can, for example, have this form. Doesn't have to have this form, can also look different, but that's a typical form. Then I need to iterate over all features that I observe in one observation, in one laser scan or in one camera, stereo camera pair. So I iterate over all observations. If the landmark has never seen before, I simply initialize it with the function that I used. So just initialize the landmark location. Because I had no idea where it is. So I had all the values, I put to 0, and I'm basically replacing those 0 values now with my observation, because it's the best thing, the best information I have about this landmark. Then I need to compute the delta, the Q, and the expected observation, exactly as we did it before. Right? So just using those expressions. Then I again need to specify my large matrix F, which you wouldn't need if you do this in MATLAB, because you would just write those individual dimensions already in the right position of your Jacobian. So you would have a large Jacobian, which is a matrix containing only of zeros, and then you would set those 10 elements directly. It's probably the way you would do it. And then I just do copy-paste from the algorithm, put the things in there. I do this for all landmarks, for all observations separately. So every feature is updated in this way. Feature 1, feature 2, feature 3, feature 4, if I see those 4 features in one image, for example. If I have 10 features I see in my image, I execute this loop 10 times. Which gives me my updated belief, and I'm ready to go. And that's it. I'm done. That's the Kalman filter, kind of the basic algorithm for the Kalman filter in the, for the simultaneous localization and mapping problem with point landmarks in the 2D world. If you would go to a 3D world, the state vector needs to be expanded, so I would have 6 dimensions for my robot or my sensor location, and I would have 3 dimensions for every landmark. The Jacobians get slightly more complicated because you have more nonlinear components in there, but all in all, it will be, you can follow exactly the same steps and would end up there. So one of the things, if you do the implementation for that, is, so sometimes people do the measurement update in a single step so they don't iterate over them, although mathematically, so depending on how many features you observe at the same point in time, this can make sense or may not make sense, but I wouldn't give this actually too much weight here. What is important for the implementation is always normalize your angular components. So be aware of the wraparounds of your angular components. So there's something, if you implement that, you need to make sure, because you're doing a linearization, and if you're at whatever, pi minus pi, you have the wraparound, you need to take care of not introducing mistakes here. So you need to make sure that you always normalize your angles into whatever, from minus pi to pi, or 0 to 2 pi, depending on how you represent it. It's something which is important if you do this, because you're linearizing your nonlinear functions, and this can get messy. The other thing is, if you do implement this in MATLAB, you may not explicitly create this matrix, this F. You will just update the individual dimensions of the matrix you just created. But that's rather clear. But if you want to put it into a mathematically correct form, it's easier to do it like this. That's it. We're done. That's it. That's what EKF SLAM is about. It's not more complicated than that. Are there any questions about this at the moment? Yes, please.
Das waren ja alle diese vorgestellten 4 Beispiele, waren ja alles Langsamfahrende. Wie weit funktioniert das mit der Rechengeschwindigkeit und schnelleren?
So, computational speed for fast-driving vehicles. This basically depends, so all the speed of the EKF basically depends on the number of landmarks you need to represent. So if you go to all those equations over here, okay, let's stay with this one. The key thing which matters is how many landmarks we can store. If you want to store 1 million of landmarks, this is not going to work. If we only store the last 10 or 20 landmarks, we can do this very fast. So it's basically how many computational resources do we have available, and if you implement that smartly, it typically grows quadratically with the number of landmarks you need to represent. So it's an n square operation, approximatively. So some elements are a little bit more expensive. There's inversion in here, but the inversion of this matrix is only the dimensionality of the observations. So it's not all landmarks, but if you restrict it to a small number, there's a chance that you will see all 10 landmarks at the same point in time. So EKFs can, for example, be used today for doing incremental updates like visual odometry. So you track a couple of features in the environment, you're moving your camera very fast through the environment, and you restrict it to, let's say, the last 20, 30, 40 features that you have seen, and you do this estimate. Then it's very fast, you can use it easily at frame rate for those cameras. If you want to maintain large maps of the environment, this is not going to work. But the same holds also if you treat everything as a largely square problem. If you have millions of dimensions, this also gets very slow. So there's always the question, do I consider the whole state space at the same point in time? Do I decouple that? So there are also variants of the Kalman filter where the overall process is decoupled into small maps. You basically build a large number of small maps, let's say always taking the last 100 features, and you're building just kind of a lot of local maps, and later on you need to fuse those local maps. So there's a lot of techniques in order to make this Kalman filter framework fast and faster than it would be if you would use the implementation presented here. The real bottleneck is the number of features that we have in here. But you can do this for fast-moving vehicles as well. Number of features needs to be reduced then. Yes, please.
On this example, we were only working with velocities.
Yes.
And so we need the time to calculate the position, because depending on the time how long you drive, you have a different position.
Yeah.
And the uncertainty in the time measurement, where does this?
Uncertainty in time measurement is not considered here. So we assume to have discrete time steps, and we need to take that into account. So the Kalman filter generally has some issues with delayed measurements. So there are advancements like delayed state Kalman filters. So also if you have measurements which come in at different points in time. So let's say you have one sensor which comes at a high frame rate like an IMU, and another sensor which comes at a lower frame rate, you actually need to take that into account. So what you typically do, you need to actually basically undo some of the operations until a point back in time, then integrate that measurement, and then redo all the computations. So there are several variants of the Kalman filter which try to take those things into account. But we assumed here so far, if you work with velocities, is that there's no uncertainty in that estimate. So typically what you do is you try to timestamp as accurately as possible, and then, but still the sensors will not fire at the same point in time, so you will do some time interpolation. So you typically interpolate the odometry information or the control information to the point in time that the measurement was taken, and then use it and just do kind of an extrapolation or interpolation between measurements. That's how it's typically done in reality. But of course, having a bad timestamping can screw up your system quite substantially, because you're basically taking wrong linearization points, wrong mean estimates, and this can actually screw up your system, especially if it's systematic. So if sometimes something is slightly delayed, it's not that bad. If you have systematic errors in there, that can be problematic. Okay, so now I've presented kind of the techniques of the Kalman filter, the vanilla Kalman filter. I now want to just use the remaining part of the time to discuss a few of the properties of this algorithm. The first thing is something which is called loop closing, which is basically done explicitly, but the effect of loop closing is always kind of remarkable if you see that for the first time. So let's say I'm a platform, I start here, I observe my very local surroundings, I drive around, I drive around, I drive around, I do a loop through the whole lecture hall, and then I actually come back from here, at the all new parts of the environment, I see it, and then I come back to the point where I've been before. So I start re-observing something I observed for a long time back in the past. Basically, was typically referred to as closing a loop. And this dramatically reduces uncertainty in the estimates, because I'm re-observing something I've seen before. And this reduces the uncertainty of all landmarks on the way. So this is an example. So you started over here, so this is the definition of the reference frame. We moved around here. So the crosses are the real landmark, the crosses are the landmark estimates, these kind of small black dots. I'm not sure if you see them, it's kind of the real poses, but the real poses don't matter right now at the moment. And these blue ellipses are the uncertainties of those landmark locations. So started over here. In the beginning, you're very certain because you have a good sensor. As long as you move, your uncertainty increases, because you have uncertainty in your motion. So you're moving and you get more and more and more uncertain. And then the robot reobserves parts of the environment it has observed in the beginning. So it will actually link those landmarks through the off-diagonal elements. And then the uncertainty of all landmarks substantially decreases. So in the next timestamp, the uncertainties will substantially decrease here because you're basically localizing the platform again using those landmarks over here, which then reduces the uncertainty. But still, the largest uncertainty I then have now somewhere over here, because I kind of propagate the information through that graph from this side and this side. That's what basically happens. So I have the largest uncertainties in here. Kind of this thing of shrinking those uncertainties is something which is called the effect of loop closure. So those loop closures reduce the uncertainty that I have in my estimates. But one of the things is those loop closures, if they do them wrongly, so if I would do a mismatch in my observations that, oh, I didn't actually enter here, I actually entered here, all the estimates are very likely to be inconsistent because I have a wrong update, a wrong loop closure. And this is one of the problems with wrong loop closures. Wrong loop closures often leads to filter divergence. So if I make this data association, I need to be actually quite certain that this data association is right. Wrong data associations, outliers, are very harmful for those systems. As a result of that, what most real-world implementations do, they don't execute this loop closure immediately. They just wait a little bit and see if I see more landmarks, so that more landmarks mutually agree. And kind of you have a kind of a pending list of loop closures. And then once you're certain enough, you actually integrate them in order to avoid those wrong loop closures. If you're now mapping through an environment, the next thing that you can see is that all the landmarks get fully correlated. So these kind of the locations of the landmarks, the robot pose and landmarks, and we just draw lines, and the thickness of the lines indicates the correlation of those landmarks. You can actually see that they're actually fully connected graph. Some are stronger, some are weaker, depending if I've seen them at the same point in time or when I've seen them. What's interesting, they all get correlated. There's a full correlation between those landmarks, which makes sense. If you take one landmark and shift it, like God tells you where the landmark is, the whole map would shift as well. So if you have your estimate and someone tells you, so God tells you this landmark is at that location, you could update the whole map. You can also see that in a small example. So you have a robot driving around, taking observations. These are landmark locations. And this expresses the correlations between the individual dimensions. And you're driving through the environment, observing those features. So these are the Gaussian estimates illustrated over here. You continue proceeding. Then you actually get in your correlation matrix this weird pattern. So you get kind of this checkerboard pattern. What does this checkerboard pattern tell you? So you have to walk around through the environment for a couple of times until this checkerboard sees this checkerboard nicely popping up. What does this checkerboard pattern mean? We're basically looking into kind of from dimension 4 to the end. What does the checkerboard pattern mean? So this is always x, y, x, y, x, y, x, y locations of the landmarks. Yeah?
The x coordinates are correlated more between each other than x and y coordinates.
Exactly. So you have basically all the x coordinates of the landmarks are correlated and all the y coordinates are correlated, but they're typically not correlated with each other. Therefore, I said you need to drive around and see all the landmarks from different locations to kind of lose this correlation between x and y. But once you nail that down, all the Gaussian estimates are only correlated in x and y. So it means if I fix the x location, so if I externally provide, okay, this landmark over here, the x location of this landmark, I nail down now, so I provide the ground truth location. That means I know all x locations because all the x locations are correlated, but I don't gain any information about y, the y coordinate. If I fix the y coordinate, the same holds in the other way around. So this checkerboard pattern means all x locations are correlated and all y correlations are y coordinates are correlated, but there's a small correlation between x and y. And if I look, as these are all checkerboard, there are also checkerboards on the main diagonal, and this means that the shapes of these uncertainties plot here are more or less circular, spherical. So these are not ellipses, I mean, they're close to a circle. Because they're also on the main diagonal, we have this checkerboard structure. That means x and y are not correlated. Okay? So given that there are a lot of correlations over here, you cannot ignore those correlations, otherwise you will get overly confident. So a couple of techniques try to ignore those correlations to be fast, even maintaining a large number of features, which is related to your question, how can we make the things really fast? And some of the techniques said we just ignore those correlations between landmarks. But this is actually not going to converge, so those approaches are typically too optimistic in the end and lead to wrong estimates because we can't ignore those correlations. If we look to the uncertainties of those landmarks, so what you see here plotted is the points in time, and basically the uncertainty of those landmarks. And this is for every individual landmark. So we start with some uncertainty. As soon as we get measurements, the uncertainty always decreases, always decreases. So all the plots are kind of decreasing uncertainties for the landmarks. And this bump here is when the landmark has first been seen. It's kind of the initialization of the landmark. It is large. So observe it a few times. Uncertainty decreases, 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 decreases. And in the end, they typically all converge to a small value because the uncertainty continuously decreases. One of the things that we see is that it doesn't reach zero. So one of the reasons is I typically may not have observed them often enough. The other thing is it depends how the platform location is initialized. If we do the initialization as we said before, saying we are in 0, 0, 0 with perfect certainty, or if I, for example, use an initial GPS location to initialize the first pose or provide some external reference. And then the uncertainty of this initialization is the lower limit. So if I have an initial uncertainty of the platform, or the first action that the platform does actually moving forward without increasing the uncertainty, that's the limit of where I can go. So the uncertainty of the platform when taking the first observation is a lower limit for the uncertainty that the landmarks can reach. So for example, if this is my initial uncertainty in the beginning of the platform and I observe the landmarks with a very noisy sensor and I continue and map this over and over again, infinitively long, the uncertainty of those landmarks will never drop below this initial uncertainty of the platform when taking the first observation. This basically means if I don't know from where I was recording, no matter how accurately I can record, I will have this initial uncertainty involved. So you do a couple of experiments, one of the kind of frequently used data sets for evaluating those things. So you take the poles used for Hürdenlauf, actually I have no idea what it is in English, and place them over different badminton courts and then drive around because you have very perfectly measured badminton courts. So you have a pretty good estimate where those poles are, and the poles are in the landmarks. You can actually drive around. This is the odometry estimate that you get. And in the end, you get a good estimate. So this is kind of all the those poles. You can estimate those. So there are some of the data sets which are frequently used for evaluating your data sets. And let's say if you have done a good estimate, if you're overly confident because you know the ground truth locations over here. In terms of the complexity of the EKF that we have. So in generally, we have a cubic complexity because we do a matrix inversion over here. Or cubic, so O of n to the power of 2.4. So the fast inversion algorithms today run at O n 2.4. But still, cubic complexity. But the thing is, if we look to the EKF implementation here we use for SLAM, we see things. So the cubic complexity depends only on the measurement dimensionality. And depending how my measurements, if I just observe a small number of features or have a low dimensional measurement, especially if I here just observe local features, let's say 2 dimensions, range and bearing, this cubic complexity does not matter. What I however need to do is I need to maintain all the covariance matrix, and this is quadratic in the number of features. So I have a quadratic number of memory that I need to maintain my Gaussian belief, because I need to maintain this covariance matrix. And I have a cost per update step, or per step, and this is how this is set up in a quadratic complexity. So I have these matrices, which are mainly consisting of zeros, so I can do most of the updates efficiently, but in the worst case, I really need to update the full covariance matrix, which is a quadratic number of elements, and this leads to this quadratic complexity that I have in here. So if you want to make things fast, we need to find a way to limit the number of features that we need to maintain. And that's kind of the key things to make this efficient. So for the EKF SLAM, what we can show is that we converge to the optimal solution in case everything is Gaussian, we live in a linear world, because that's the Kalman filter is the optimal estimator, which is something we don't have in the real world, or it's very unlikely to happen. If we have serious nonlinearities, or we have extremely large uncertainties, we've seen this in the Kalman filter as well, then the estimate of the Gaussian distribution under our nonlinear function may deviate substantially from the true mean and the true variance. And therefore, we may diverge if we have serious nonlinearities in there. Of course, we have only a single Gaussian estimate, so we cannot handle multimodal distribution. So I'm either here or there, which actually happens, especially for indoor mapping, or can happen quite frequently. In general, we can say the Kalman filter is today not that frequently used anymore for solving those SLAM systems, just because of its complexity with respect to the computational complexity and memory complexity in terms of the number of landmarks that we have. But it's still frequently used if I either have a limited environment or typically if I have used it for short-term estimates. So for example, for visual odometry. So I take into account only the last, let's say, 100 features, and I build an incremental estimate estimating where I am, just kind of doing SLAM on the last 100 features and forgetting all the rest. So I just interested in getting a good incremental estimate. That's still a technique where EKF SLAM or something very similar to SLAM for incremental pose estimation is still frequently used. But there are a lot of variants of the Kalman filter trying to reduce the computational complexity. One of the things was breaking things down into submaps. So always taking whatever n features, building a submap, and then simply starting a new submap when my computational resources are over. And then maybe I can later on align those submaps with a least square approach, and I have just a very small number of nodes that I need to consider. These are all things which you can do in order to make the EKF faster or computationally more tractable. So there's a large number of different variants that can be used in here. That's it from my side. Again, there are a large number of literature about EKF and EKF SLAM. All the notations, all the algorithm, how it is done here is again done according to the Probabilistic Robotics book, chapter 10 on EKF SLAM, which is a very good read to dive more into the details and see all the elements. I tried to explain everything you need actually to implement something like this on your own, but if you need further explanation or think that I failed in explaining something, that's the first reference to look at. What we've done now today is provide a technique which is actually very similar to what we do in bundle adjustment or general least squares approach, estimating the location of our sensor and of features in the environment in order to come up with an estimate. The main difference is here we do incremental pose estimation in an online fashion. So we are only interested in estimating the current location. We're not interested in the whole history as we have done this for bundle adjustment, for example. Of course, there are also variants of the bundle adjustment approach which try to estimate only the current pose, ignore the past, or marginalize out features. So these actually are two techniques which sit on both sides of the spectrum. So on the one hand side, you see the EKF, which is in the Gaussian linear case, that's exactly the same, or gives the same solution in the bundle adjustment. As soon as you have non-linearities, you need to relinearize. Therefore, the bundle adjustment works better than the Kalman filter because it doesn't relinearize. And depending on how much of the history you forget or use in terms of poses, you're actually moving from bundle adjustment towards the EKF. So if you would ignore all the old poses, you move to a solution that's actually very, very similar to the EKF. So you can see those techniques as being two sides of a spectrum. One taking all the information into account, one taking only the current information into account, but there's actually the whole field of intermediate things you can actually do. You can actually vary depending on the computational resources that you have. And there are a lot of techniques which try to vary this bound. So in some situations, it's good to have a short buffer of feature that I estimate. Sometimes I want to do more, maybe doing this hierarchically organized. So there's a very large amount of literature trying to get good estimates as fast as possible, as accurate as possible, and depending on the direct needs that you have for your application, you may choose within this kind of large spectrum or zoo of different algorithms in order to perform this estimation. That's it from my side for today. Is there any remark or question about EKF SLAM and incremental pose estimation? So if this is not the case, thank you very much for your attention. There's one final remark regarding the exam. So what the topic that I have not addressed this year, which I did last year, was the unscented Kalman filter, which is a variant of the Kalman filter to better deal with the linearizations. This is something which will be dropped. So there was a very large exam or a larger exam question last year. We haven't discussed this year, so this will be not part of the exam. So UK, even if you look to the old recordings or the old lectures, there is UKF will not be part of this exam. The rest of the material basically stayed exactly the same to what I've taught last year. And there was also the question before, we have this tutorial, and from my point of view, the tutorial is a pretty good preparation for the exam. So it's from this, of course, the questions are not exactly the same or not exactly the same questions, but they are done in exactly the same spirit as I expect what you should know for the exam. So they're not done as something like, use this to learn what I expect you to learn in the course, but the exam will be completely different. This is not at all the case. So it was intentionally made as a good preparation for the exam. That was kind of at least the goal. And yeah, that's the thing I wanted to add at the end.